So far in this course, we've learned about a number of very interesting nonlinear devices. We started with a diode and saw that with that simple device, two-terminal device, we could already do a lot of interesting things that we couldn't do with linear devices. Then we introduced two types of transistors, and we saw that, again, the inherent nonlinearity in the input-output characteristics of those devices. For example, BJT had an exponential nonlinearity, or MOSFET had a quadratic nonlinearity. Those nonlinearities allowed us to use them in a lot of interesting applications, such as amplifiers. So we noticed that it's not too difficult to, these two devices were used as current sources, controlled current sources. And we saw that by using the right combination of resistors actually around these devices, it's not that difficult to convert the current into a voltage signal and get a relatively large gain if you want to use them as a voltage amplifier. BJT had an inherent gain of beta for the current if you applied the signal to the base and take the output from the emitter or collector. A MOSFET had an infinite input resistance, which makes your life easy in a lot of situations. And by biasing these devices in their active regions, we could make them sensitive to small changes at the input and therefore make amplifiers. We could also use them as switches. We could use a MOSFET in its triode or cutoff regions as on or off switches respectively. Same thing with BJTs in saturation or cutoff regions. And therefore, we could perform logic operations, and you saw that for BJTs and MOSFETs in your labs. Now, that basically lets us make any type of amplifier you want for any application. However, as a designer, as a user, or as somebody that wants to just make an amplifier for a routine application, designing amplifier circuits with transistors involves a lot of work, involves a lot of thinking. You have to worry about the variations in beta or temperature or the threshold voltage between these devices, and then make sure that they meet your bandwidth requirements, power requirements, all sorts of different parameters that are important to a circuit designer. And people since the early days have been looking for finding ways to make that whole process a bit easier. Today we are going to introduce a new device. It's called an operational amplifier, and we'll see that if you just learn this one device, you should be able to satisfy more than 90% of your circuit design requirements in future. So later on, if you are designing a mechatronic system and you want to interface a sensor whose output impedance is such and such, and you need a gain of such and such, you can design it with OpAmps most likely, very easily and much more quickly than what you could do with a transistor. It doesn't mean that we don't need the transistors anymore. We see that OpAmps have their own shortcomings, and in many cases you would use an OpAmp in combination with a transistor amplifier. But for basic cases, for I would say 70 to 80% of situations, a single OpAmp can do the job for you. And as we'll see, it can do it much, much more easily than thinking about a proper amplifier based on transistors. One good thing about an op-amp is that you can actually look at it as a linear element. It's just a device that multiplies the difference between two signals at the input and puts it at the output. How it does that, by this time you know that there is a complex circuit inside that package that is sold to you as an op-amp, where a combination of transistors and maybe resistors and sometimes capacitors is used to give you that functionality, to make the whole circuit behave as if it is just a linear element multiplying a voltage difference by a certain gain. So for a typical op-amp, this is the symbol that we use. A basic op-amp, when you look at the circuit equivalent or circuit model, is just this. You have two inputs, a non-inverting input and an inverting input. And And for a basic op-amp, this is the basic relationship. V out is A times some gain, some voltage gain, times V1 minus V2. That's what an op-amp does. A linear device, it looks at the difference between two signals and multiplies it by a gain value. Now, again, because we know that there is no such thing, you cannot make these out of resistors and capacitors and things like that if you want to have an increase in the signal power. We know that, the way the magic happens inside that box is through the power of some nonlinear elements, some transistors. In the early days it was tubes, nowadays it is transistors that take the power from your DC source and add it in through those nonlinear characteristics that they have, add that power from a DC source into an AC signal, and therefore you can have a signal at the output whose power is significantly larger than the input. So while this is the symbol for an op-amp, we know that at the very least an op-amp needs to have at least 2 extra pins. So you have your V1 and V2 as before, but you need to provide bias. So if you want to be explicit about that, you show the 2 bias pins like this. Or VCC and VEE are the naming that we have, let's say, inherited from the BJT days. Nowadays, actually, MOSFET op-amps are more common, so you may see VDD and VSS instead of VCC and VEE. Normally, for the sake of simplicity in your analog configurations and analog operations, you would like to use a positive and negative supply. So you use a plus 3 volt and a minus 3 volt supply, plus 5 and minus 5, plus 15 and minus 15. So VCC and VE are usually the same value but the opposite sign. But there are situations, and they are increasing actually, where you do not have a negative supply, right? So for example, if you're powering your circuit with a single AA battery, you just have 1.5 volts, and you usually do not split it into plus 0.75 and minus 0.75. So you just have your VEE, maybe your ground, and then you just have a positive supply. If possible, using a negative supply usually makes your life easier. You can get past the AC signals and keep them around 0, and just the whole bunch of analog signal processing operations that follow that are going to be simpler. You don't have to worry about the DC levels. But as I said, sometimes it's not possible, or it may be more economical to just use a single supply for your device. So VEE may be a ground connection, but VCC is your typical power supply, and in most cases, as I said, you have both the negative and positive supplies. If you go to really, really old days and pick some really, really special purpose op-amps, they have more than 2 power supplies, but nowadays you're good with 1 or 2 supplies. Now, one quick note here, and we'll come back to how to select an op-amp hopefully by the end of this discussion. If you're choosing an op-amp for an operation and it's a single supply operation, make sure that you use a single supply op-amp, right? So not all op-amps are able to operate using, let's say, a ground connection for VE and a positive signal on VCC. They are specially designed. Anyway, so at the very least, we know a practical op-amp has to have 5 pins, 2 for power supply and 3 for the signals. Now, what is an ideal op-amp? So if you look at an ideal op-amp, this is how we define an ideal op-amp. Operational amplifier, for short, we call them op-amps. The first thing about an ideal op-amp is that it has an infinite gain. So infinite differential gain. So if you look at that expression at the top over there, that means that A naught is really, really large. What does infinite mean practically? if you pick OpAmps from a data sheet of a manufacturer, normally the gain, that open loop gain, we call it also open loop gain, is on the order of hundreds of thousands to a few millions typically. So infinite differential gain. So any difference between the two signals, between the two inputs, is amplified with a very large gain. What is the second the requirement? It has zero common mode gain. So what does that mean? It means that if V1 and V2 are equal, if they have the same potential on them, common mode signal, that is the op-amp gain for that common mode signal is 0. So it doesn't amplify what is common between the two signals, it only looks at the differences between them. The other property of an ideal op-amp is that it has an infinite input resistance. Okay? So we saw that if you have a voltage amplifier, an amplifier that the signal that is coming to it is a voltage, an infinite input resistance is very helpful in most cases. In most situations we would like to have an infinite input resistance. And what that does is that, remember that when you have a source with some output impedance, the voltage at the input of the amplifier is the voltage division between Rin of the amplifier and Rs of the source. Now, if you have an infinite input resistance, Rs of the source doesn't matter, right? You get all of the signal from your source at the input of your amplifier, and your amplifier can do the amplification then. So for an ideal op-amp, this is another property that we assume. Another property of an ideal op-amp is zero output impedance. Or let me just call it resistance. Okay? So again, when you look at the op-amp, the signal at the output is a voltage, so it's acting as a voltage source, and for an ideal voltage source, you would like the output resistance to be 0. So for an ideal op-amp, that's what we would like to have. And then the final thing about an ideal op-amp is that it has infinite speed. What does that mean? It means that whatever happens at the input, it immediately reacts to it. Right? There is no delay, there is no warm-up time, there is nothing. As soon as some changes happen at the input, the op-amp reacts to it. We haven't discussed issues related to speed that much in this course. These are related, speed in time domain and frequency response. They're related to each other. For the op-amps, we'll actually talk about that a little bit at the end, because it becomes a major consideration, design consideration, if you're using a circuit with op-amps. But an ideal op-amp has these properties. Infinite differential gain. The differential gain is also called open loop gain for the reasons that we'll see soon. It has a zero output impedance, zero common mode gain, infinite input resistance, and infinite speed, extremely fast. Okay, so this is an op-amp, ideal op-amp. And now let's see what happens if you want to use an ideal op-amp in a circuit. Okay, so let's see what will happen. So assume that this is an ideal op-amp. I have some sort of a configuration around this op-amp. I have my power supply, let's say VEE and VCC, or VDD and VSS. And there is an output signal that comes from V1 and V2, the difference between V1 and V2. So I know that V out is your open loop gain times V1 minus V2. Okay, the difference between those two signals. So that's what we have for an op-amp. For an ideal op-amp, there is an interesting case. So I know V out is bound by VCC and VEE, right? So again, going back to our transistor amplifiers, you know that the circuit, when you have just resistors and capacitors in a transistor amplifier circuit, and let's say the devices are in their active regions, none of the voltages anywhere in those nodes in your circuit may go above your power supply, either at the top end or at the bottom end, right? So the voltages can never increase or go beyond VCC, or they can never drop below VEE. So V out is bound. It has a finite value, right? So if VCC and VEE are plus or minus 5 volts, V out is going to be between those values. So if you look at that practical limitation and rewrite that equation as this, V out over A naught, knowing that V out is limited by some finite value and A naught is going to infinity, this approaches to 0, right? With A naught going to infinity, the difference between V1 and V2 will be 0. What does that mean? It means that an ideal op-amp will do all it can, for as long as it stays in its linear region, for to ensure that V1 and V2 are the same, right? V1 and V2 track each other. If you make a change in V1, the op-amp will go through, whatever magic that is happening inside, will go and ensure through the circuitry that is around the op-amp. You usually have a resistive network. It ensures that V2 follows V1. The difference between these two will be very, very small. Usually, practically, it's not measurable, so it is 0. That is one interesting conclusion. So V1 and V2 follow each other, right? So what this means is that if you have an ideal op-amp that is working linearly, V1 is following V2, right? V1 and V2 will be equal. We'll show you how this happens, right? So for now, yeah, so you can always say that, okay, I go and use a signal source V1 and an independent signal source V2 and apply them to the input of the op-amp. Then what? Well, what is going to happen then is that your op-amp is going to leave the linear region. It's not going to behave as we discussed so far. So the output is not going to be the difference of the two signals times gain, because the gain is infinite. Usually your output voltage from the op-amp will be either saturated at the top or the bottom, and that's it. So you can force a difference between the two, but if you let the circuit do its job, and let's say you apply 1 voltage to V1 and then let V2 settle on the right value, V2 will be equal to V1. For this reason, it's called as if there is a virtual short. Right? So the circuit behaves as if there is a virtual short circuit between V1 and V2. What does that mean? Why do we call it virtual? So I'd like you to maybe spend 1 second thinking about why is it called a virtual short? What is the difference between this and a real short circuit? In a real short circuit, if the two nodes in the circuit are shorted to each other, the voltages follow each other all the time. Similar thing is happening here. And why do we call it a virtual short? What is the difference between this configuration and a real short? I'll come back to that in a second. And maybe this part that I'm going to explain will help you answer that question. The second rule, so this is rule 1. This, we call it the first golden rule for linear op-amp circuit analysis. And we'll see how it is applied. The second point that we note is that if you go back to the list of ideal op-amp properties, there is the issue of infinite input resistance. So if R in for your op-amp goes to infinity, remember that I can draw any voltage amplifier as long as it is linear. I can simplify it to something like this, right? and I just put this whole thing inside a box and sell it to you as an amplifier. But inside it, it could be a combination of maybe tens of transistors. But at the end of the story, as long as it is behaving linearly, I can reduce it to something like this. And for an ideal op-amp, you know, A in this case is infinite, and R in is also infinite. Now, there is a current going into this terminal for that input amplifier, right? And we saw that actually, in order to figure out what R in is, you attach a test source there, measure I in, and then R in will give you, the current is then giving you, the ratio of the two gives you the input resistance. However, if R in is infinite, well, something interesting happens. Immediately, I don't know, you can see that I in is 0. If R in is infinite, I can conclude right away that I in is, or must be 0, regardless of the input signal, right? So as long as my op-amp is in its linear region, I in is 0. This condition actually holds in most cases, not all cases, even if the op-amp is not in its linear region, right? But this second rule here, so this is the second rule, this is rule number 1, rule number 2. This second rule holds even if the op-amp is not in its linear region. And the reason for that is that, let's say at the input of that op-amp, I'm using a pair of MOSFETs. MOSFET, the gate current is 0, regardless of the operating region of the MOSFET, for example, right? But keep these two in mind. This is rule number 1, that for an op-amp in a linear region, and we'll see why when we can keep it in a linear region, the voltage at the two terminals follow each other. And this is the second one. The input current to an op-amp terminal, either positive or negative or inverting or non-inverting, is 0. Now, with these two simplifications or these two conclusions from the definition of an ideal op-amp, we can solve these op-amp circuits very, very easily. Now, going back to the question that I had earlier, that why do we call it a virtual short, I think you should be able to see that by this point. It's a virtual short because there is no current between these two inputs, right? In a real short, you can have any current going from one node to the other in either direction. We call this a virtual short because although the two voltages are equal to each other, there cannot be any current going between the two terminals, right? The two nodes are physically separated from each other. So let's go and look at one application. So I'm going to talk about a circuit that we call inverting amplifier. So this is the configuration. I have an op-amp, and I do not draw the power supplies anymore, those two connections for the power supplies any longer, because we know that they exist, right? So it depends on what type of op-amp you use, but we know they exist, so there's always some power supply to provide the power that you need for the operation of the circuit. Okay, this is a very well-known circuit called an inverting amplifier, right? So we'll see why. So if you want to analyze this circuit, I notice one thing, right? So from the first rule that I have, I know that V plus is equal to V minus, right? So the voltage on the inverting terminal is equal to the voltage on the non-inverting terminal. However, the inverting terminal is grounded. If you look at this point, the inverting terminal is grounded. So from here, I can see that V minus, or the voltage at the non-inverting terminal, must be 0 if I make this device, if this circuit using ideal op-amps. Okay, if the voltage here, so I put a symbol for a ground here. I call it a virtual ground, and we'll see why it is called a virtual ground. So it is 0 volt, but it's not a real ground. Again, think about it. Why is it called a virtual ground? What is the difference between this 0 volt and the 0 volt that I have at the non-inverting input at the bottom? I have a 0 volt at the inverting input and also a 0 volt at non-inverting input. The non-inverting one is a real ground. I call the other one a virtual ground. And if you answered the reason that I call it a virtual ground is that there is no current going into that ground, that's correct. The second rule says I into the op-amp terminal is 0. So a real ground would take any current or provide any current that you want depending on the rest of the circuit requirements. In here, it just provides a fixed voltage. You cannot change, you cannot send or receive current from that terminal. Okay, but that is good because now I can calculate this I1, let's say. So I1, if I want to figure out how much it is, I have 0 volt at one end of that resistor and V in at the other end, so it's V in minus 0 divided by R1. Now because I in is 0, all of this I1 has to go through R2. The current that is produced at the input cannot go into the op-amp. All of it has to flow through R2, and that makes it easy because then I can see that for the voltage drop across R2, I can say 0 minus V out, right? That's this voltage drop, is equal to the current through it, so it's I1 times R2. And rearrange this, I can see that for I1, I just put V in over R1 and put the negative sign on the other side, so I can see that V out is minus R2 over R1 V in. Excellent. We got a gain using just 2 resistors without worrying about biasing, changes with temperature, anything, right? As long as your resistors are stable with temperature and, let's say the ratio is what you want for the gain, you've solved your amplification problem. You have a negative sign in front of the expression. That's usually not important, but we'll show you a different circuit that will even take care of that. Or you can use 2 of these one after the other, chain 2 of them to get rid of the negative sign. But really simple way of making an amplifier. Just 2 resistors, 1 op-amp, done. Now I'd like you to think for a second about what happened here. What happened here is that the op-amp that you used created that virtual ground in your circuit at the, let's say, middle node between R1 and R2. And by doing that, what we could do is that we could faithfully convert V in into a current. So the current here is just proportional to V in divided by that resistance, right? So what this circuit did is that converted the input voltage into a current. And then because the op-amp doesn't take any current, what we did is that we rerouted the current through R2 and just again Ohm's law let us create a V out that is proportional to R2, and because I1 is proportional to R1, we got an output signal that is proportional to the 2 resistors. But the main point here is that we found a way to accurately convert a voltage signal into a current, and then that's not difficult, right? So you could do that with any resistor that is grounded in your circuit. You could always convert the voltage signal into a current using a grounded signal, a grounded resistor. However, what the op-amp let us do that now is that once we created that current, it let us reroute it, right? And use that current, and basically we multiplied that current by R2. But it let us reroute that current. And I'll show you another circuit right away that takes advantage of this amazing property of this circuit. I'm going to ask you to figure out what the input resistance of this circuit is, this amplifier is. The output resistance, I'll tell you right away, it is 0. You're looking at the output of the op-amp. But what is the input resistance of this whole amplifier? If I look at this entire box as one amplifier, what is the input resistance there? Right, so if this entire thing is inside the box and I sell you the box as an amplifier with a gain of minus R2 over R1, what is the input resistance of that amplifier? So do that and then maybe ask me during the live session if you want to check your answer. But let's do an example. So we saw that this amplifier already does something really amazing, just basically giving us a gain with 2 resistors and that's it. Let's see what else we can do with this circuit. Consider this new circuit. So the question is, what is V out for this circuit, right? So now we have 2 independent voltage sources applied to the op-amp through 2 different resistors. We have a feedback resistor around the op-amp, and the question is, what is the output voltage? So what I'll do is that I go back to my circuit theory. I recognize that this is a linear circuit, so I should be able to use superposition. So I apply superposition. Right? It's a linear circuit, right? So it is a different condition than what we had for most of the situations in this semester so far. So set, let's say, V2 to 0, right? In superposition, you apply the sources one at a time. So you apply one source, zero the others. When you zero a voltage source, you basically get a short circuit. So I get a short circuit here for V2. And then if I do that, I can see that in this case, well, I have my virtual short between these 2 inputs. Therefore, I have a virtual ground connection here. With the virtual ground, I get 0 volt here. It's not ground, it's 0 volts. If I have 0 volt here, I have 0 at this end of R2, 0 for V2, and therefore R2 really doesn't play any role in this circuit. I am back to my original circuit. So V out is minus RF over R1 V1. Do the same thing for V1. You can see that V out is minus RF over R2 V2. And then combine, right? You can show that then V out is equal to minus RF times V1 over R1 plus V2 over R2. You can have a bunch more resistors down here for different inputs, and then this just keeps going. Okay, so what did we make here? Right here in front of you is an analog adder. And the good thing about it is that it's a weighted adder. So you can combine multiple voltage signals that may come from different sources. You can give weights to different voltages according to your requirements, and add them up using this circuit. It's an analog adder, right? So what happens? Well, the only issue is that you get a negative sign in front of your adder, or in front of the output from your adder, but the output is the sum of A1, let's say V1 plus A2 times V2 plus A3 times V3 plus A4 times a V4 and so on and so forth. And those A's are the ratio of those RF and the resistor that you put between the voltage source and your op-amp. Fantastic, right? So if you want to do any analog signal conditioning, this could be a very useful component. So for example, you may have 5 sensors in this room, and you want to take an average of those 5 readings. So let's say each sensor is producing a voltage signal for you. You want to take the average of those 5 readings and just send it off to some sort of a reader or display. This circuit easily lets you do that. So just choose RF to be 5, and R1, R2, and R5 that you will use for those 5 sources. Choose all of them to be choose RF to be 1, and R1 to R5, set them to 5. It could be 1K, and those guys could be 5 kilo ohms. So what happens is that the output of this circuit, you will have 1/5 of V1 plus 1/5 of V2 plus 1/5 of V3, and so on and so forth. And therefore you get your average right away without doing any computation, any calculation in almost real time, right? And this is one advantage of analog signal processing to digital signal processing. Even nowadays, considering that we've had about 100 years of, not exactly, but 80, 90 years of digital computation history, and despite the fact that digital computation is very, very easy, you perform the operations that you want in code. Even nowadays, if you want to do something really fast, really quick, and sometimes with the least amount of power that is possible, you do it in analog domain. So in a lot of high-end applications, the signal processing is still done in analog domain. And you need building blocks. So if you want to do addition of signals, subtraction of signals, you want to do integration and differentiation. We'll talk about those in a second. You need building blocks, you need computation blocks, and this is a simple example of what you can do, or how to do that, right? So, and then one more point here is that just think about for a second that how did this happen? How did we get a signal? Why did we get a signal at the output that is the sum of those inputs? How is this happening? And if you go back, well, the math says so, right? So the KVL and KCLs tell you so. So that's really not an interesting answer. But if you go back and think about what we said for the inverting amplifier, what you're doing here is that you're converting V1 into a current, converting V2 into a current, converting V3, V4, all those signals into a current. And if you want to add currents, it's super easy. You can add currents at a node. So what you do is that you convert all those signals into currents, bring them here to this node, add them up. Now the input resistance that is infinite for the op-amp, or the current that is 0 for the op-amp, lets you that current that you've created from the addition of all those, lets you reroute it through RF and produce a voltage signal that is proportional to that current. So again, it is helpful to think about, having that virtual ground and a resistor somewhere as a way of generating a current that is accurately representing your voltage signal. Okay, so now let's talk about a different type of an amplifier here with an op-amp. Let's say that you're for some reason bothered with that negative sign and you want to get rid of it. So there's going to be a different category of amplifiers. It's called a non-inverting amplifier. And this is the topology. similar to the inverting amplifier. But in this case, I keep this end of R1 grounded and apply my signal to the non-inverting input directly. Okay? So same arrangement, but what I'll do is that I'll create, I'll switch the location of ground and signal between the two terminals. Now, if I want to analyze this circuit, I look at this circuit, I want to use the golden rules that I have for the op-amp. I know there is a virtual short between the two, so first thing that I notice is that V plus must be equal to V minus if the op-amp is in its linear region. Therefore, I can see that V minus has to be equal to V plus, and that's V in. So the voltage here is V in. Okay, so I mirrored that voltage to that node. Now that I know the voltage here, well, I look at resistor R1, I know the voltage at one end of it, I know the voltage at the other end of it, I can calculate this current. So this current I1 is going to be V in minus 0 divided by R1, or just V in over R1. All right, good. Now because the current that I have at the input of the op-amp is 0, all of that current should go through R2. Okay? And I can see that between the two sides of R2, I can write the equation. So V out minus V minus divided by R2 is I1. Plug in what I know for I1 and V minus. I can see that V out minus V in, remember V minus is equal to V in, divided by R2 is equal to V in divided by R1. Okay? So multiply both sides by R2 and move V into the right side of the equation. You can see that V out is equal to 1 plus R2 over R1 times V in. Another great simple expression. Now I have a gain that is positive. It's always larger than 1, right? So 1 plus R2 over R1, that ratio is always 0 or larger. And the gain is positive. If I want a gain of, let's say, 100, I choose R2 over R1 to be 99. If I want a gain of 2, I choose R2 to be equal to R1, and so on and so forth, right? So if that negative sign for inverting amplifier bugged you, or you didn't like it, here is another option, an alternative option with a positive gain, right? So that's why it is called non-inverting amplifier. It doesn't invert your signal. Now there is another advantage to this circuit, and that's where you consider the input resistance, right? So when I look at this circuit, I'd like you to go and think about it and tell me what the input resistance of an ideal op-amp is. Convince yourself that in terms of input resistance, this circuit is superior to your inverting amplifier. In most cases, I'm not going to say in all cases. Okay. And we can check your answer during the live sessions as I mentioned before. Now, let's look at a common example for a non-inverting amplifier. It's, let me draw the circuit again. In many analog applications, you want a circuit that lets you measure a voltage or take a sample of a voltage without the voltage at that node being disturbed. So it's like you have a voltmeter or oscilloscope and you want to measure the voltage at a node in your circuit, but you don't want the oscilloscope or probe of the voltmeter to load that node. You don't want the voltage at that node to change when you touch it, right? Because as soon as you touch it, remember, the voltmeter that you're using, the probe that you're putting here is going to effectively put the equivalent resistance, the input resistance of that probe, is going to add it to that node. So if that input resistance of the voltmeter is comparable to the impedance in that node, you're going to change the voltage at that node. So let's say if the equivalent resistance down here is 10 kilo ohms and the input resistance of your probe is 10 mega ohms, well, if you put a 10 mega ohm resistor in parallel with the 10 kilo ohm resistor here, nothing is really changing by much. The error that you produce by touching that node with the probe is negligible. But if you have a high impedance node, so the equivalent impedance here is, let's say, 1 mega ohm, and you touch that node with a 1 mega ohm probe, then the voltage at that node will immediately drop by a factor of 2. So whatever you read on the voltmeter is not really the actual voltage here when you remove the probe. It's going to be half that, right? Or a fraction of whatever it should have been. So in many cases in electronics, you would like to have a circuit that sits between your measuring system. It could be a microcontroller, it could be a voltmeter, it could be anything, right? And whatever that you're measuring, but what you want from this circuit is to faithfully translate the voltage from that node into something that is, or somewhere that is easier for you to deal with it and not affect the voltage over there. So what I can do is that if I look at this circuit, I remember that V out is 1 plus R2 over R1 times V in, right? And if all I want is a faithful, true reflection of that voltage of V in at the output, I can see that, well, I can easily do that in two ways. I can make R2 go to 0, right? And then I get V out equal V in. Or I can make R1 go to infinity. And in that case, infinity means that keeping it an open circuit. And in that case, I achieve the same thing. Or I can do both. And this is going to be the circuit that you have. So this is called a buffer, or a voltage buffer, right? And what it does is that it creates a voltage at the output that is hopefully exactly equal to V in, but for whatever that you're putting here, what they see is an infinite input resistance. There's zero current being taken from that. However, over here, you can take as much current as you want because the op-amp has a zero output impedance, ideal op-amp, and therefore you have a voltage source over there, zero output impedance, draw as much current as you want. You can measure that voltage and connect it to a speaker and make sound out of that signal, right? Without your source even knowing about it. So this is a very common signal, very practical, and you see them a lot. And then, next time that you see this and you think, why would anybody need a gain of 1? If it is a gain of 1, how is that a voltage? Why do we call it an amplifier? Well, there are two reasons that we may use a circuit like that. The first one is, well, the infinite input resistance and zero output impedance, or output resistance. But there's also something that I'm implying or getting to without even telling you the exact thing. But think about it. Why do I call it an amplifier if the voltage amplitude does not change? If the voltage at the input and output are exactly the same, equal to 1, the gain is equal to 1, why do I call this an amplifier? Is this an amplifier? So think about it, and I'd like to just convince yourself that this indeed is an amplifier. So now that we know these two basic stages, you should really be able to satisfy a lot of your practical needs for amplifiers with these two stages. And then you have the combinations or derivations from those two stages, right? So for example, you can have the weighted summer or adder using this circuit, You can have a buffer using this circuit. These are basically simple derivations of the same circuit that you saw before. Let's look at another interesting circuit using OpAmps. So in this case, what I do is I make this circuit, apply two signals to it, and then the question is, what is the output voltage here, right? So again, because this is a linear circuit, what I can do is that I can use superposition. So set V2 to ground, right? So let me maybe and if I do that by setting V2 to ground and noticing that this current is 0, then I don't have any current through R3 and R4. Therefore, the voltage here will be 0. Or ground, well, I'm not going to draw ground here. It's going to be 0, right? So this is 0 volts, and because of the virtual short between these two, I will have 0 volts over there. I'm back to my basic non-inverting circuit, so the output is just going to be minus R2 over R1 V1. Good, easy. Now set V1 to 0 and then see what happens next. So if I set V1 to 0, let me use a different color here and get rid of this. Then by setting V1 to 0 and applying V2, I can see that the voltage here, oops, what happened? The voltage here is going to be a voltage division between R4 and R3 proportional to V2. Why? Because again, this current is 0. Since that current is 0, the voltage at the node between the two resistors is going to be just a voltage. We can find it through the voltage division rule. If you draw any current from the middle point of two resistors, you cannot use the voltage divider rule anymore. But because the op-amp gives you a 0 current at that point or has 0 current at that point, then I can find the voltage at the inverting input from voltage division. So R4 over R3 plus R4 times V2. Now that I know the voltage at that node and V1 is grounded, well, the rest of the circuit is the basic non-inverting amplifier. I already know how to solve that, so I can show that V out is just 1 plus R2 over R1 times V plus, which is R4 over R3 plus R4 V1. V2. And therefore, if I combine the two results, V out is going to be minus R2 over R1 V1 plus 1 plus R2 over R1 times, I'm going to divide the numerator and denominator for the second fraction by R4, so 1 plus R3 over R4 times V2. And you'll see why I did that in a second, okay? So that's good, right? So I have a circuit now that can subtract two signals from each other. What is the weight for each one of those signals at the output? I just set using the resistor values, R3, R4, and R2, R1, right? So if I want to have, I don't know, 5V1 plus 10V2, I can just go and see if I can do that using these proper ratios here, right? But there is a special case. So let's look at the special case where R4 is equal to R2 and R3 is equal to R1, right? So if I just use two resistor values, then what happens is that this ratio here is going to be okay, and then for the second fraction, so R1 plus R2 over R1 times 1 plus R3 over R4, do the math, you can actually show that it's going to be 1 plus R4 over R1, but R4 is equal to R2 plus R2 over R1 times V2, right? Or I can write it as R2 over R1 times V2 minus V1. All right? So in that special case where R1 and R2 are, R1 is equal to R3 and R4 is equal to R2, we actually have a circuit that amplifies the difference between the two signals, V1 and V2, right? It subtracts those two signals from each other, and if you like, you can have a gain. You can have an R2 over R1 that is larger than, let's say, 1. You can have a gain of 10, 100, 1,000, whatever that you want, okay? So that's great. I introduced a circuit to you a few minutes ago that can add analog signals to each other. And now you have a circuit that can subtract analog signals from each other. And that's great. So basically, you can now do a lot of mathematical functions. You can see, multiplication, for example. If you want multiplication by a constant, you can use an OpAmp circuit and multiply a current by R2. That gives you a multiplier or a voltage gain, right? So it could be a multiplier. You have adders, you have difference amplifiers. Now, you can also divide signals. If you say, if I want to multiply by a constant gain less than 1, you can still do that. You can make a circuit to do that. But it is also possible to make circuits using OpAmps to do other types of mathematical functions on signals. So you can have a circuit that multiplies two signals by each other, or takes the logarithm of a number and or a signal and put it at the output, or puts the exponential value proportional to the input signal at the output. You can do all sorts of those things with an OpAmp circuit. We talk about some of them later on, but basically with an OpAmp you have all the tools you need for analog signal processing. I'll talk about the making integrators and differentiators in a second, and with those circuits you can solve differential equations in analog domain. So you have an integrator that takes the integral of the signal, you can multiply. You can do that many times. You can have 5 integrations of that signal. And by combining these derivatives and integrated signals and adding them with proper weights to each other and subtracting them from each other, you will have the ability to solve a differential equation in analog domain in real time. There's no need to wait. There's no need to calculate anything. There's no need to worry about, let's say, convergence or anything like that. You just apply your input signal, let's say it's a sinusoidal, and the circuit solves it for you and put the corresponding solution at the output. We'll talk about that later on in this lecture. Now, the difference amplifier I'm showing you here is great with one shortcoming. That is practical. In theory, there's really nothing wrong here. But in practice, you usually have some output resistance for V1 and V2. They come from a signal source. And those two output resistances may or may not be equal. You may or may not know them. In most cases, you want to have some safeguard at your end of the business, in your circuit, to make sure that those variations in properties of V1 and V2 do not affect what you intend to do with your circuit. You basically want to subtract V1, V2 from each other and multiply that by the difference by gain. And in cases like that, there is a challenge, there is a difficulty here. Because for V1, the input resistance is R1. For V2, the input resistance is R3 plus R4. Or if you use the R3 and R4 that are equal to R1 and R2. So for V1, the input resistance is R1. For V2, the input resistance is R1 plus R2. So you have asymmetry between the two inputs. And even if your V1 and V2 are exactly the same with the same output resistance and also all that, they will see different input resistances when they look at your amplifier, your difference amplifier, and that affects the output of your circuit. So to go around that problem, we improve this circuit by adding a couple of buffers to it. So what I do is I make my difference amplifier. This is the block that does the subtraction of the two signals for me. I need that. All right, so because I want it to be, let's say, so let's say this is V1 and this is V2. So this is my R2 over R1 times V2 minus V1. So this is my difference amplifier as we just saw before, but I want to protect that function, what I'm getting out of it, from the variations in the input resistance of the amplifiers that go, or the sources that go before it. So what I do is what I learned before, that if I want to have a true representation of a voltage signal, I can use a buffer. And same thing here. Okay? So now then these two can be VI1 and VI2. I get them from anywhere in the circuit. What the two buffers over there do is that they take those signals regardless of the source impedance and put them at those nodes at the input of the difference amplifier, and then the difference amplifier sees a zero impedance source, the output of the two OpAmps before it, and then just V1 and V2 therefore, and then amplifies them and produces the output at the as shown over there. So this is great. Now I have a circuit that takes the difference between the two inputs, and this is a very, very, very important circuit in instrumentation and measurement. That's why it has its own name, instrumentation amplifier, where you, for example, want to measure the voltage across a resistor. So one input goes below, one input goes above the resistor, so that you measure that voltage difference, right? It has its own name. And this is the instrumentation amplifier. However, what you can say is that, well, so as long as I'm using two op-amps to make the buffers, I may as well get some gain from them. So what you can do here is that instead of just connecting the two outputs to each other, what you can do, let me move VI1 to the top here. And we'll see the reason why in a second. It just makes my drawing a bit simpler. So let's just get some gain out of this guy. So let me draw it like this. So let's say you can call these R4 and R3. And same thing for the guy at the bottom, right? So you can so the two buffers that you had at the input, if you need the gain, you can actually get some gain from them as well. Just use a non-inverting amplifier instead of a regular buffer. And in this case, what you can see is that the output voltage is going to be proportional to the difference between the two inputs. Good news here is that if there's any common mode signal between these two, it's going to be rejected by this topology, right? So if V1 and V2, so let's say if VI1 I don't know why this thing is playing games today. So if VI1 is, let's say, 1 volt DC plus A sine omega t, and VI2 is just 1 volt DC, the output here is proportional to just the A sine omega t part, right? Or if it is, let's say, 1 plus 0.1, right? So 1.1 volt at one input and 1 volt at the other input. It rejects the common mode part, the 1 volt that is the common mode, and it only looks at the difference, which is the 0.1 volt, right? So this is called an instrumentation amplifier, very, very useful in instrumentation and measurements. And then what you can do is that you can look at the differential behavior of this circuit. That you say, okay, it's only responding to differential signals. So what does that mean? It means that the signal here goes up, this goes down. Differential means they move in opposite directions, right? So the way to rewrite this as a sum of the differential and common mode signals, you can say that VI1 is 1.05 plus 0.5 and VI2 is 1.05 minus 0.05. So you have a common mode part that is this part, and you have a differential part that is this part, right? So plus point, so the parts that are moving in opposite directions are this little one over here. And you can show that if that's going to happen, you know, you're only interested in the differential signal. If you go and instead of grounding these two middle points, you just connect them directly to each other, you still get 0 volt in here, right? It's not ground, it's a 0 volt, right? Why? Well, think about it. I'm going to make it an example here. So think about it. You have one resistor here, equal value. This voltage goes up, this voltage goes down. You know, what do you think this voltage is going to be? For a differential change at the two ends of these two resistors, that voltage remains 0. So without connecting that middle point to 0 volt, you actually get 0 volt between them, right? And then what happens next is that, well, you have two resistors in series. Why do you need two resistors in series? So what you get in a typical differential instrumentation amplifier is a direct connection between the two inputs with just one resistor. So let's just call it RG. And you know that, you know, practically when it is used, RG is basically, you can divide it into two resistors, series resistors, RG over 2, and then basically you have your input gains and some voltage gain for each one of the two amplifiers, and you have your difference amplifier next. this is a very important amplifier, as I mentioned, in most analog applications. So that is going to be it for today. For this lecture video, what I'm going to discuss next is what is going to happen if we have a complex impedance around the op-amp instead of just resistors. So maybe if I have Z1 and Z2 instead of R1 and R2, then what happens and what we can do about this amplifier.